The definite integral is a really important topic in calculus, and I want to use an example to explain how it works. So here's an example. The rate at which snow is falling t hours after midnight is 0.05 t inches per hour. Estimate how much snow has fallen by noon. So this is a total change problem. I want to figure out what's the total change given the rate of change. The rate of change is given by a function. The function is 0.05 times t. Okay, so we can estimate this with overestimates and underestimates like we did before. And to do that, let's first put our data into a table. So I'm going to sample what happens at t equals 0 hours, t equals 3 hours, 6 hours, 9 hours, and then at noon, 12 hours after midnight. So according to this function, at 0, 0.05 times 0 is 0, so the number of inches per hour is 0. Snow's not falling at all. But 3 hours later, at 3 a.m., we have a rate of 0.15 inches per hour because 3 times 0.05 is 0.15, and then we can fill in the other tables just using this formula. So we get this table, which represents the number of inches per hour that are falling at a given time, and we want to get an upper estimate on how much snow falls in this 12-hour period. So what do? You can use an upper estimate. So for each interval, 0 to 3, 3 to 6, 6 to 9, and 9 to 12, I can use the upper number, the larger number of the two numbers over that interval. And in the 0 to 3 range, I have an upper estimate of 0.15. That's bigger than 0, so I use 0.15. 3 to 6, I use 0.30 instead of 0.15 because 0.30 is bigger than 0.15. And then I use 0.45 for the next interval. And for the last interval, I use 0.60. And so here's that sum that gives me the overestimate. And this overestimate tells me that at most 4.5 inches fell between midnight and noon. Do the same thing with the lower estimate, except this time we're going to use the numbers on the left because these are the smaller numbers. Between 0 and 3, the small number is 0. Between 3 and 6, the small number is 0.15. Between 6 and 9, the small number is 0.30. Between 9 and 12, the smaller number is 0.45. And so I use these numbers to sum up to give me the total change in the snow. An estimate, it's an underestimate, so it says that at most 3.0, at least 3 inches of snow fell between midnight and noon. So somewhere in between 4.5 and 3.0 is the truth. And so you might ask, okay, so how do I get a better estimate on what's happening? Well, if you can go to smaller subintervals, you can always get a better estimate. It's very much like the derivative. Smaller intervals, better. So what I mean by smaller intervals? Well, let's instead of choosing intervals of length 3, here all my intervals are length 3, let's go to length 1. I can generate a table using my function for intervals of length 1. So what does that table look like? Well, here it is. So I have everything going up from 0 to 12, but now my intervals have length 1. And I evaluate my function at each point. And I do the same thing as I did before, upper estimates and lower estimates in the same exact way. But now I have a sum of 12 things instead of just 4. And when I sum these things up, if you do all the work, you get 3.9 inches. So that's an upper estimate of 3.9 inches. That's a much nicer estimate than that 4.5 estimate. It's a little smaller, but it's closer to the truth because we have as a lower estimate 3.6. Okay, so the truth actually lies between 3.9 and 3.6, whereas before, when we used 4 intervals, the truth lied between 3.0 and 4.5, which is much bigger. It's a difference of 1.5. Here, the difference is only 0.3. Gives us a much better idea. Okay, so can I do better? Well, yeah, you can make these intervals as small as you want. Instead of using length 1, you could use length 0.00001. And in fact, this is how your calculator is going to compute, or at least approximate, these kinds of sums, give a good estimate. Eventually, if you take it small enough, then these two numbers will be the same. And that fact is a very nice fact, and it allows us to find something called the definite integral, which is what we want to talk about here. The definite integral is when you take really tiny intervals, infinitesimally tiny intervals, that gives you a sum. Both lower and upper estimates are going to be the same, and it's going to be equal to something called the definite integral. the definite integral of the function f of t over the interval between, well, in this case, what do we have? We start at 0 and we end at 12. So over the interval between t is bigger than 0 and 12. So this gives us, in particular, this is going to tell us the exact amount of snow that falls in that time period between midnight and noon. Now this is a lot of words to remember, so we use some notation to represent this. So instead of writing that, I'm going to write 0 to 12, and then I'm going to write f of t dt. Okay, what are these things? Well, actually the f of t should be colored blue because it represents values of the function, like I've been using before. And what the heck is that dt thing? Well, the dt is actually the length of the subinterval, and it's infinitesimal. We don't actually have a length anymore when we take the limit, but it represents sort of this length here. In this case, the length is 1, but we're going to actually, dt is like 0.00000, infinitely many zeros, 1, right? So that's going to be really small. So that's the definite integral, and 0 to 12 is our interval. This funny S shape is just something you have to live with, and this is what we're going to have to deal with, is this type of thing. And your calculator will be able to compute these. We'll also be able to compute these later in Chapter 7 using the methods that Newton gave to us. Let's look at what happens geometrically in this situation. How does this definite integral, what's its geometric interpretation? Well, here's the interpretation of those Riemann sums that we saw in the first part. These are the upper estimates and over estimates. In particular, let's focus on the upper estimates. The upper estimate looks like this, and in terms of geometry, it's the area of these rectangles. The area of the rectangles is the upper estimate. So the area of the rectangles is 4.5. It's the upper estimate. Okay, but what if we took smaller intervals? Intervals length 1, we get something like this. And now here, this is going to be the other upper estimate, which is a better estimate, which is 3.9. This is upper estimate when you use smaller intervals. It's closer to the truth. Okay? And what is the actual definite integral? Well, when these little sawtooth things are gone, they disappear. We don't want sawtooths. We actually want just the area under the curve. So if we take the area under the curve, which is this triangle, that's the actual definite integral. It's 0 to 12 of f of t dt. Okay, in future videos we'll explain more details about this.